Hey, what's going on? This is Riffy. I'm going to go over senses hearing with you guys real quick. So there's a PowerPoint right here that normally I just post. So we're going to give this a whirl, and I'm going to lecture through to you through this PowerPoint. Uh, so here we go. So hearing is actually relatively simple, and your hearing is kind of divided based on the structures and what goes on in each of those structures. So it's kind of divided into the external ear, the middle ear, and the inner ear. So the external ear basically just simply consists of your auricle, which is just what you would consider the cartilage portion of your ear right here. And its main purpose is simply to collect sound waves and funnel them into the external auditory canal. So sound waves traveling through the air get funneled in, and you can increase that funneling by cupping your ear like this, which basically just simply increases the size of your auricle or your actual cartilage form of your ear, funnels them into the external auditory canal where they're actually sent into towards the middle ear. Most of the time, you can pick up sounds just simply through air, because that's how all sounds, unless you're in water or things like that. But if you've ever been in water, you notice you can actually hear sounds that are a little distorted based on the fact that the sound waves travel different through liquids when they have actual waves traveling through them. But that's another story. The other purposes of the external ear is that it protects the opening to the external auditory canal. You have a couple things that help out with that. You have what are called ceruminous glands. They secrete cerumen, which is just earwax. The purpose of earwax is it prevents foreign material from entering. This can be anything from simple as water to microorganisms, and it helps reduce the chance of infection. And if you've ever had an ear infection, you know how painful those are. And if you've had one as an adult, you can actually know that, and it can cause things like vertigo. But you also have hairs, believe it or not, they increase with age, that provide the same function to preventing the things from entering your ear and the growth of microorganisms and things like that, even though they are slightly unattractive. So what you have here is you have your auricle, or your outer ear, you have your ear canal, and you have ceruminous glands which secrete cerumen or earwax. Now of the three parts, the external ear actually ends at what is considered to be the tympanic membrane, which in other words is your eardrum. Here I have a nice, very graphic picture or diagram showing a Q-tip poking through your eardrum. Yes, when you clean your ears out with Q-tips, you can actually shove the Q-tip in far enough to where you can touch the eardrum. And if you push a little too far, you can actually shove that Q-tip right through your actual eardrum, which is quite painful. It's called a ruptured eardrum and causes sounds to be distorted and all kinds of things, which we'll learn about here in just a second. Sound waves, as they're collected and they're directed into the external auditory canal, they reach the tympanic membrane. You literally think of it as a drum. When you take a stick and you strike the top of the drum or the pad of the drum, it changes the energy in the actual stick of a drumstick into sound waves. Well, here we're actually taking sound energy waves and changing them into mechanical movements. So when sound waves reach your tympanic membrane, your eardrum, it actually causes the energy in the sound waves causes the tympanic membrane to move back and forth, and it creates additional waves. So once those sound waves reach the tympanic membrane, it's now considered the middle ear, which is the second of the three main structures of the ear. So from here all the way in the external auditory canal to right here, your tympanic membrane, this is your external ear. The middle ear would be considered from the tympanic membrane, including the auditory ossicles in this section right in here. In the middle ear, you have the three tiniest bones in the entire human body, and their main function is to simply help transmit sound energy waves that were changed in the tympanic membrane into what are called mechanical movements. So there are three bones that move not through necessarily the aid of muscles, but simply from movement due to sound waves that help transfer that energy into the inner ear, which actually helps generate the action potentials so your brain can interpret sound. The three smallest bones are actually called the malleus, the incus, and the stapes. You have the hammer, the anvil, and the stirrups are the common names, but those aren't really used anymore. And we are going to call them the malleus, incus, and stapes. You can actually see that this one looks like a hammer. If you have the handle of the hammer here and the head of the hammer, This is the anvil, which a hammer is, you know, a hammer hits the anvil. And the stirrups look like stirrups. The malleus itself is attached to the tympanic membrane, which then connects to the incus, and the incus connects to the stapes. So if it's a continual series of bones and membranes that are connected to each other, when one moves, it results in movement of a second one. So it's a simple transfer of sound waves into mechanical energy waves throughout the middle ear. So when a sound wave actually strikes the tympanic membrane, it causes the tympanic membrane to move. This movement then causes all the auditory ossicles, those three bones, the malleus, the incus, and the stapes, to be displaced in the correct order from malleus to incus to stapes, moving in towards the internal ear. When sound waves are way too intense, there are actual muscles that are attached in your middle ear to the tympanic membrane and the ossicles that can prevent them from moving so much, because believe it or not, some sound waves are so intense, either in such high frequency or such high amplitude that carries so much energy, that if you did not have those muscles, just simple sound waves could cause a rupturing of your tympanic membrane and possibly even the breaking of the auditory ossicles. So when a sound wave is funneled by the external ear into the external auditory canal and striking the tympanic membrane, there's two ways we kind of interpret sound. How high or how low a sound is based on the frequency of the sound wave. Frequency is how often a wave strikes a surface. So if I draw a wave that looks like this, and this represents as a time frame 1 second. What that means is the frequency of waves is there are 3 waves striking the tympanic membrane per second. That's the frequency. Now, how loud the sound wave actually comes through will depend on the amount of energy carried in the wave. So if we have the same frequency of sound wave, representing 1 second yet again, but the wave size is significantly bigger, the same sound is produced because the same frequency or the same number of waves occurring in 1 second is exactly the same. But what is different is this bottom one is significantly louder because the waves are carrying more energy. Volume, like I said, is determined by the amount of energy. So you could have two sounds that are the exact same sound, but one is louder than the other simply based on the amount of energy carried in that wave. So when I increase the volume of my voice, even though it has the same pitch, it's louder because of the increased energy in the wave. So with an increase in energy or an increase in volume, that's why your ears actually hurt. It has nothing to do with the fact that it might not be high-pitched or low-pitched. It has to do with the fact that it is carrying so much energy and striking your tympanic membrane, and it's actually causing pain. So what we have here is a little bit more detailed version of those muscles. You'll see that there's a muscle attached right here, which connects kind of to the tympanic membrane. There's a muscle here that attaches kind of to the malleus. There's a muscle that attaches to the stapes right here, and it kind of prevents them from actually moving with super increased energy sound waves. The middle ear is also connected to what is called the nasopharynx, or you would call that the eustachian tube. And a lot of people ask, I get this question a lot, your ears are actually attached to your nasopharynx, which then attaches to the back of your throat. So your ears, your nose, and essentially your throat or mouth are all connected to each other. Now, what is the purpose of having an internal auditory tube or eustachian tube that connects to your nasopharynx? Well, if you think about it this way, you have air that is outside here in the external auditory canal. Believe it or not, you also have air inside of here. Well, when the pressure of the air changes here, that's where in the external area, that's where you get what is called the popping of your ears. You feel that intense pressure pushing on your eardrum. Well, the eustachian tube, or this internal auditory canal right here, one of its main purposes is actually to balance the pressure inside of your ear with outside of your ear, so you don't have damage to the auditory ossicles or the tympanic membrane. Again, here's just another picture of that right here. External auditory canal, tympanic membrane. It does have some disadvantages though. If you look at this picture right here, the most common age group for ear infections has to be the infant age group. And if you do just a simple anatomical comparison of an infant to an adult in terms of the internal or eustachian tube right here, you will notice that the eustachian tube in an infant has more of a flat, or it lays more flat than it does with an adult, which is more angled. The laying of it being more flat actually allows foreign materials to pass from the nasopharynx into that eustachian tube, things like bacteria or anything like that, which results in what are called inner ear infections, which are, from speaking from a father of a 5-year-old and 2-year-old, tend to be some of the most painful things for an infant. Adults don't have that problem as often because the eustachian tube is in fact bigger and it does have a greater angle to it, so inner ear infections don't happen as frequently. Okay. Now, with the middle ear, and you have the malleus, the incus, and the stapes actually attaches to the inner ear at what is called the oval window of the bony labyrinth. So in terms of complicated processes, the inner ear is actually a lot, or significantly more complicated than the outer ear and the middle ear. Here we have a picture, again, the outer or external ear includes the external auditory canal and the pinnae, or the cartilage portion of your ear. You have your middle ear, which includes the tympanic membrane, your 3 auditory ossicles, and the eustachian tube, or internal or inner auditory canal. The inner ear is going to basically be where the stapes right here connects to the cochlea or shell, which also will include the 3 semicircular canals, which, if you remember, we talked about those in our balance and equilibrium lab. They have a fluid inside of them that spins that actually allows you to notice rotational movement and monitor the position of your body. You also have nerves that for monitoring balance and equilibrium that attach right here, but you also have the vestibulocochlear nerve, which attaches right here, which is actually the one that's in charge of sound. A little bit more magnified here. Everything from this area all right here is the inner ear. Middle ear, tympanic membrane, and everything out here is the external or outer ear. The bony labyrinth is divided into 3 parts. You have the vestibule, you have the semicircular canals, and you have the cochlea. The cochlea is the actual portion that is involved in interpretation of sound waves. The vestibule and the semicircular canals are involved in equilibrium. So the cochlea is, by definition, shaped like a snail shell. It contains receptors for hearing and is divided into 2 chambers. You have the vestibular duct and you have the tympanic duct. Don't worry about those too much because that's a little bit more detailed when you want, but the 2 chambers are separated by the cochlear duct in the middle ear. So here's your semicircular canals, you have your cochlear nerve, you have the cochlea, and here's the snail shell looking structure. Here's where balance is, and here's where your equilibrium or semicircular canals. Here's a little bit more detailed structure, or it's got a mid-sagittal cut to it, so you can actually see where the stapes attaches in here and sends sound waves in. And they, believe it or not, they travel around the entire snail shell, and they exit the sound waves because what you'll learn in a second is pressure is generated. It has to be relieved in some way, and that is through the round window. Anyways, so when the malleus, the incus, and the stapes move, the stapes is the last bone that moves. That stapes is attached to the cochlea at what is called the oval window. I want you to think about when you're in a swimming pool and you're on a raft and somebody moves the raft up and down in the center of the swimming pool. That up and down movement causes waves to radiate outward. The stapes works in the same direction. When it moves in and out of the oval window, it creates pressure waves inside the cochlea that travel through a liquid called perilymph, and it travels through the vestibular duct, which disturbs the cochlear duct. The cochlear duct has what are called, for lack of better terms, hair cells attached to neurons that, when they are stimulated, transmit action potentials. Those action potentials converge on the vestibulocochlear nerve. That nerve goes directly into the brain, particularly the medulla, which we'll cover in 1 second. So if you see the malleus moves, the incus moves, the stapes moves, right here is the oval window. When this stapes moves in and out, it creates waves that travel throughout the cochlea. And the distance, or how far a wave can travel before the energy is dissipated, depends on the frequency of the wave and the amount of energy carried in the wave. Actually, it just depends on the frequency of the wave. Here's what hair cells are going to look like. If you notice, they have they kind of look like the bars on a cell phone, but when they are disturbed or tilted to the side, that's the absorption of the waves in the perilymph, and that stimulates those or creates a difference in the membrane potential, which sends signals down through the nerves, generating action potentials being sent to your brain. Now, the frequency of the sound is determined by which part of the cochlear duct the hair cells are stimulated. Remember, frequency is how low or how high pitched a sound is. The volume of that sound is determined by how many hair cells are stimulated. So if you look at it this way, this is a cross-section of your cochlea. Remember, the oval window is where the stapes attaches and creates pressure waves that travel in. So when an incoming sound is created, it creates the pressure waves in the perilymph of this particular canal right here. If you notice, it's divided based on the number of hertz, or how high the frequency of the sound is. So as it travels through here, you will notice that sound waves travel and disturb the basal membrane, but we're not going to get too much into that. And travels, and as it gets higher and higher and higher, it actually travels further and further and further, disturbing more and more at a higher frequency or hertz, 4,000, 5,000, all the way up to the maximum value of 20,000 hertz, which is typically the high value of human hearing. All the pressure waves in the perilymph that are generated here can be relieved through what is called the round window. Another look here, malleus, incus, stapes, generating pressure waves that travel throughout the cochlea and out the round window. Round window, oval window, sound waves in, and then back out through the round window. Something I forgot to mention, throughout these canals are hair cells that actually get disturbed based on the frequency of the wave and the amount of energy that is carried in it, and that's where the higher low pitch sound is interpreted. And they are sent down the vestibulocochlear nerve, right in here, to your brain. Now, the information or action potentials that are generated by the hair cells, like I said, are transmitted through neurons that converge on the vestibulocochlear nerve. That attaches right back here. You will have a quiz over all these structures that I've just gone over. The vestibulocochlear nerve reaches the medulla oblongata, and if you remember, one of the functions of the medulla oblongata is it distributes signals throughout the brain. It routes them to where they need to go. And that is sound. This PowerPoint is also posted on my website. These YouTube videos here that I have linked are all videos that can help you out in reinforcing any of the information that I've given you. Just like always, email me if you have any questions. I appreciate it.